Welcome to this lecture for Research Methods. We'll be talking today about one-way experimental designs. So what we'll go over, a little review of terminology, talk about what things need to be present in an experiment to allow for causal inferences, and then talk a little about a particular type of one-way experimental design, or within subjects design, and then a little bit about evaluating the use of experimental designs. Okay, terminology. One way. What do we mean one way? Well, one-way designs are ones where there's one way that groups are made to vary, right? So there's one independent variable. If you have more than one independent variable, you could say it's a two-way, but more frequently, as we'll learn, you'll call that a factorial. So if you have 2, 3, 4, anytime you get past one independent variable, it goes from a one-way experimental design to a factorial experimental design. So there's one way they differ. They differ on, if they got the drug or no drug, 10 milligrams, 20 milligrams, 30 milligrams. Still, they differed on how much drug they got. There's only one thing they differed on, right? One variable. So in that one variable, as we've already said, is the independent variable. That's the one that the experimenter manipulates, right? And it's said to have different levels. Sometimes instead of levels, we talk about there being different experimental conditions. Any experiment has a minimum number of levels, right? You have to have at least two. You can't say, okay, I'm going to give people a drug and see what happens. Well, you got to give some people not the drug, right? So there's always at least two levels of the independent variable. And when you have levels, typically you're creating groups of people that are at the different levels that are receiving different levels of the independent variable, right? So that's the one you're manipulating. And then the one you're measuring is the dependent variable, right? Where in most experiments, we're looking at a cause relationship where we hope that what we do to you, how we manipulate you, what we do in terms of the independent variable, will have an effect on something else. So your score on this other variable will depend on what we did to you. And so the score on the variable that is depending on some other variable, well, that's the dependent variable, right? So that's the one we measure. Talk about two basic types of designs: between subjects design for an experimental study, and that's where your different levels are different groups of people, right? So each participant in an experiment that's in a between subjects design receives only one level of the independent variable. So if it's a drug study, right, with 0 milligrams, 10 milligrams, or 20 milligrams, if you're a participant in that study, you're only going to get one of those things. You're only going to get 0, or you're going to get 10, or you're going to get 20. You won't get all three levels. You just get one level, right? That way you're looking at this group versus that group versus that group. So comparing between groups, between subjects. Or you could have a within subjects design where participants in an experiment receive all levels of the independent variable, right? So we're going to give you no drug, measure the dependent variable, see what happens. We'll give you 10 milligrams, and then we'll measure the DV, see what happens. And then we'll give you 20 milligrams and measure the DV again, see what happens. So we have three different measures of the dependent variable after you receive each of the three possible levels of the independent variable, right? So within subjects design, people receive all levels of the IV. Between subjects, you receive only one level of the IV. All right, so experiments, again, the primary reason we use them is when we're looking to make causal inferences. So to make a causal inference, three things need to be present. One, there has to be some association, right, between the DV and the IV, right? Where there are differences in the dependent variable that are associated with differences in the independent variable, right? We do this thing to you. Well, now you're different on the DV than you were when we didn't do the thing to you, or when we didn't do the thing to somebody else, right? So there's kind of a correlation there. Right? And again, correlation doesn't mean causation, but if causation is there, there's going to be an underlying correlation as well because you have that association. Temporal priority. That's just a fancy way of saying, well, obviously the cause has to precede the effect. You're looking at two things, and A happened before B. Well, A could be a cause of B, but B can't cause A because it happened afterward. Right? So we look at establishing that with the design of our studies. And then to make causal inferences that you can be confident about, you also need to control common causal variables, or control those third variables, right? All the things we talked about with why you can't infer causation from correlation. So we're addressing all those things with experiments. And one of the things with correlation is, well, you have to worry about these common causal variables, this third variable problem, that there's something else that's affecting both the IV and the DV. So really what you're talking about here is you're eliminating alternative explanations for the difference you find, right? That association you find between the DV and the IV, you've got to control for things that could otherwise explain why they're related. So look a bit, that's weird, we'll look a little more closely at two aspects of this, one being association. So is it possible for there to be a perfect association? So for there to be a perfect association, that means for every instance where people differ on the dependent variable, that they also differ on the independent variable. And for every instance where people differ on the independent variable, they also differ on the dependent variable. Right? And does that happen? Well, no, probably not. Think about, does anybody really doubt that smoking contributes to lung cancer? No, I don't think anybody really questions that. There's substantial evidence for a causal relationship there. But has there ever been an instance, just one, of somebody who gets lung cancer but never smoked? Yeah, probably. Or of someone who smoked but lived a long life without ever getting lung cancer? Yeah, probably so too. So when we're looking at these associations, it's not that if this, then this every time, and if you see this, this other thing must have happened, right? We're looking at more of these causal relationships being probabilistic, right? So if a causal relation exists, then you are more likely to see certain values of the dependent variable depending on the level of the IV that you're exposed to, right? So if there's a causal relationship between smoking and lung cancer, then the more you smoke, the more likely it is you're going to have lung cancer. Won't necessarily get it because, again, things are multiply determined. But if it's having a causal influence, it's making it more likely that this thing is going to happen, right? Another thing to think about when we think about this association, because for experiments, typically the associations we're talking about are differences on the dependent variable depending on the independent variable. Well, when those groups differ, how big a difference is needed in the dependent variable? Well, more than a little bit, right? Because some difference is expected based on just sampling error, right? If you get two groups of people, and you randomly assign them to, get a drug and get a placebo, and then you measure them on a dependent variable, something you think the drug is going to affect, even if your drug had no effect whatsoever, those two groups might not have exactly the same mean score, right? Due to sampling error. There's random error in there where there happens to be some people that typically score a little higher, typically score a little lower on that the thing you're measuring. And so those samples represent populations. And again, if the thing didn't work, then they came from the same population. So their mean should be the same, but they won't always be due to sampling error. So they have to be big enough. And that's where Anova comes in, right? When you're looking at group differences. And you can look at, with two groups, you could do a t-test. You could still run Anova with that. Anytime you get beyond two groups, looking at 3 groups or more, you have to do Anova. And what Anova does, it looks at, okay, how much variance is there between these groups, right? And that's thought to be due to the treatment, plus how much error variance is, so people just being different within the groups, and then divide that by how much of this kind of error within groups variance is there, where people are just different than each other. And if there's no variability due to the treatment, then you'll just have, variance due to error over variance due to error, and your ANOVA, your F value, will be equal to 1. And F equal to 1 will never be statistically significant. Now, as you have more variability that's due to the treatment relative to that other variability, that numerator gets bigger, the F value gets bigger, now you're more likely to have a statistically significant finding. And that's what ANOVA is looking at, is, okay, looking at this variability between groups relative to the variability within groups. And this ratio, once the between groups difference gets big enough, they say, okay, yeah, there's something going on different between these groups. Okay, in terms of temporal priority, the independent variable is manipulated by the experimenter rather than us just looking at differences after the effect has happened, right? And that's how we establish temporal priority. if you're looking at, oh, I wonder what the effect is of, you know, an earthquake on people's sense of safety. And you go, right after an earthquake, you go study people's sense of safety. You may think, okay, yeah, I'm getting a good idea of what the effects are. Well, maybe, maybe not, right? Because you didn't cause the earthquake to happen. Those people may have already, if they're really afraid right now, they may have already been afraid. You don't know which came first, their fear or the earthquake, because you didn't measure them before, right? Whereas in an experiment, we're going to do something to them that we think is going to cause some change, and then measure the outcome of the dependent variable. So that manipulation of the independent variable is key to establishing that piece of temporal priority for causality. And as I already said, at minimum, whenever you're manipulating an IV, you have two levels, experimental typically, and a control. So again, something you're doing to people compared to, you know, doing nothing to them or doing something you think won't have an effect. But sometimes you may need to do more than two levels of an independent variable. Right? More than two levels, more than two conditions. And one thing this does helps answer the question, well, did the experimental condition cause an increase in the DV versus did the control condition cause a decrease? Or vice versa. Maybe the experimental caused a decrease, but the control, or was it the control caused an increase? So what I'm saying here is if you have two groups and we're having people, you know, listen to, you know, heavy metal music. Okay, well, heavy metal music versus something more innocuous, some elevator music. And we think heavy metal music makes you angrier. When we play the heavy metal music, we play the elevator music, and we measure how angry they are. And you find a difference. Well, you don't know for sure if they're angrier. Let's assume they're angry in the heavy metal group. Did they get angrier because of heavy metal? Or is everybody pretty angry and they got calmed down by the elevator music? You don't know which thing pushed the difference, right? So you may need something else in there, like, you know, no music versus elevator versus heavy metal. Right? So figuring out which thing is having the cause, if it's your control condition or experimental condition, you can look at that with more than one condition. Even more frequently, we're trying to look at identifying the functional relationship between the independent variable and the dependent variable. Right? So this is what I'm talking about. Think about drug studies, right? 0 milligrams, 10 milligrams, 20 milligrams, 30 milligrams. We can see, okay, as we increase dose on the drug, what happens to our dependent variable? Are people getting more and more happy the more drug we give in a kind of a linear fashion? Or is there a curvilinear relationship where they're getting more and more happy and it plateaus? Or does it come down and now they get really unhappy if we give too much drug, right? Or maybe there's some sort of exponential relationship where there's small changes at small dose increases. Once you get to one point, even little bitty changes will lead to huge changes in the dependent variable, right? And you can't figure that out with just two levels of an independent variable. Sometimes you need more levels to figure out really what that relationship looks like, the kind of data you would get from a correlational study, right? This is whenever sometimes maybe you're interested in those things that you may be interested in with a correlational study. You can look at a little bit with experimental study with just more levels. But again, the more levels you have in an experiment, well, the more participants you're going to have, and that becomes more costly, more time-consuming, all those things. So trade-offs. Another reason you might use more than two levels is to increase the construct validity of the independent variable, right? And again, when we talk about construct validity, often we think about the DV because we think about, oh, are we measuring what we say we're measuring? But the independent variable also can have more or less construct validity. So let's say our basic study is a drug study. I give 0 milligrams versus 10 milligrams, and I find no difference. Okay, well, maybe I didn't sufficiently manipulate the independent variable, so 10 milligrams of drug wasn't enough of the drug to be effective, so that wasn't, that manipulation didn't have good construct validity because I wasn't really representing the true effect of the drug. Whereas if I'd done 0, 10, and 20, my 20 milligram group all of a sudden shows an effect. Okay, now I can see that because I have, think about it being like more content validity for the independent variable. I've got more levels of that IV showing up. Or if I'm doing, showing people pictures of attractive and unattractive people and looking at how it influences dating decisions, right? if I have just 2 pictures of 2 attractive people and 2 pictures of unattractive people, okay, well, how representative are those pictures of all the attractive and all the unattractive people? Right? I might need more, and like moderately attractive, super attractive, crazy super attractive. I might need more levels of my IV to get a better representation of that manipulation of the independent variable. Similarly, having more than 2 levels can help increase the external validity of the findings. Right? So we're trying to say, okay, the truth of this study, how far does it extend beyond? Well, if you only have 2 levels, well, it extends to these 2 levels of the IV, these 2 levels of drug. Or if I have more levels, I can obviously extend my generalizations further. It's like, well, at 20 milligrams, this happens. At 30, this happens. And at 40, this happens, right? So I've got broader conclusions I can make, which means I have greater external validity. So a variety of reasons you may want to use more than 2 levels. With, again, the caveat being, the more levels you have, the more participants you're going to need to maintain adequate power. Okay, third thing, looking at control for those third variables. One thing you're looking to do is establish equivalence of groups before the independent variable is manipulated. Right? And this is typically done through random assignment, randomly assigning people to groups, randomly assigning people to levels of the independent variable. Now, what this does, let's say I'm looking at a study where I have some intervention. I'm going to teach some people, this thing that's going to help them be speed readers. They'll read faster, right? I'm going to teach them the tricks to one group and not the other, and I'm going to measure then how many pages they can read in 10 minutes, right? Now, in the 50 people I recruit to be in my study, there may be 5 kind of super readers in there who already read super fast. The idea behind random assignment is that not that I'm going to get rid of those super fast readers because they're going to screw up my study, but I'm going to divide them equally, where I get half of the super readers in one group and half in the other group, right? So they're kind of going to balance each other out when they affect the means of those groups, right? So if they're balancing each other out and my thing really does have an effect, well, the super readers that are in my treatment group are going to get a little bit faster. The super readers not in my treatment group aren't going to get faster. So I'll have even faster super readers than before. But for that to happen, I need a fairly large N, right? If I have an N of less than 30, random assignment doesn't have as good a chance of doing its thing and creating equivalent groups. As N gets past 30, it becomes more likely that random assignment is going to work for me, and I'm going to get roughly equivalent groups on all the variables that may have an impact on the dependent variable. So being able to do random assignment assumes you have the power to assign people to groups, the power to assign people to levels of the independent variable, which is another kind of hallmark of experimental research. You can't have people coming in already in a group, right? So I can't look at people who are widowed versus not widowed, because I can't assign them to be in those groups. They're already in those existing groups. If I can't assign them, I have no power to do that. I obviously can't use random assignment or any other type of assignment to try to establish equivalence, like a match group design. I can't do it, so therefore it's not an experiment. But in experiments, I have the power, and I use random assignment. Fingers crossed that I've created equivalence between these groups and all things that might affect the DV before I get started with my study. And then I also want equivalence kind of throughout the study, except for the independent variable, right? Where if a simple experiment where I only have 2 groups, those groups, the only way they differ is in what I'm going to do to them, the independent variable. Otherwise, intelligence, height, how funny they are, how attractive they are, how long they sleep, all these things. On average, these 2 groups are the same, right? And the things they experience are the same. The only thing that's going to be different is what I do to them. That way, if I see a difference in the dependent variable after I do something, I can be confident that, well, they're the same on everything. Now they're different on this dependent variable. They must be different on the DV because of the thing I did to them, the IV, and now I can draw that causal inference. And again, I do that by exerting experimental control. I do it in two ways. One, when I try to establish that there's, again, no difference in their experience between the groups other than the independent variable. Right? So I'm going to treat them exactly the same. So I'm not going to have, okay, randomly assigned group A and group B. Group A, you're going to go over here with Phil. Group B, go with Sheila. Okay, well now I've got Phil and Sheila. I've got a male and female experimenter working with different groups. Might that affect their behavior on the dependent variable? Maybe. I can't do that. So I've got to have the same experience as much as possible. Same type of experimenter interacting with them, same amount of time. And the thing I'm manipulating, my experimental group, make it as similar to the control group as possible. Right? So again, if I'm looking at, that's why I have that study with listening to heavy metal. Well, just do heavy metal versus nothing. Well, now I've got one group listening to music and one group not listening to music. Okay, so I can't be as confident that if there's a difference that it's caused by heavy metal. It might just be caused by listening to music versus stuck in a room being bored. Right? So the experience need to be as similar as possible, except the one thing that you think is going to have a causal effect. So you exert experimental control to do that, which often means conducting the study in a laboratory setting where you have control over those things, and you can, make the temperature of the room the same, the lighting the same, all that stuff, same. The other thing you try to do as much as possible is insulate the groups from the effects of extraneous variables that could impact the dependent variable. Right? And again, so we want to make the two groups the same, but we also don't want other things that we know might affect the DV playing a role. So again, that's one reason to be in a lab versus, oh, they're at home. They could be doing all kinds of things, right? So if I've got maybe my study of speed reading and I, watch this intervention online and then do it at home. Well, could have some people not taking it seriously, taking longer than others. Some people drinking lots of coffee, maybe some people doing methamphetamines. Who knows? But anyway, these things that could be affecting the dependent variable, right? And if those things that are affecting the dependent variable that are extraneous variables, if there's that kind of randomness happening to both groups, it's not the worst thing, right? Because if it happens to both groups, it should affect both groups equally, and it won't make me see a difference that isn't really there. But what it can do, if there's all these other things affecting the DV other than my IV that I'm not controlling for, that can add error variance. And we look at that, think back to that fraction with Anova. No matter how much treatment variance there is, if there's a whole lot of error variance at the top and the bottom, it washes out that treatment variance, and I can't see the effect, right? And that's why we try to, again, have people in a standardized setting and control for things that might affect the dependent variable that could logically be expected, at least in the short term, to affect what you're measuring. Try to protect people from that. Again, and that's again why you do many experiments are done in a lab setting rather than do it on your home at home on your own time, because error variance. Okay. Another way to establish equivalence is to use a within subjects design, right? Because if we're trying to use random assignment, make the groups as equal as possible, and we're going to treat them the same, do all this stuff. Well, another way to make the groups the same is to just have them be the same, right? So you have the same people in the experimental group as are in the control group, right? And if you do that, you're talking about a within subject design, also sometimes called a repeated measures design, particularly if you're doing a pre-post type of within subject design. In such design, you're comparing each subject to himself or herself rather than comparing two groups, right? So you're going to listen to heavy metal and you're going to listen to elevator music, and I'm going to compare your score in this group and in this condition to your score in this other condition, and I'll calculate some difference, right? If your scores are the same, the difference is 0. Okay, had no effect on you. If your scores are, heavy metal, you're more angry than an elevator. Okay, let's say you're a +2. Let's say I have two people in my study. You're a +2 and somebody else, and they're angrier in elevator music than heavy metal by 2, and they're a -2. Okay, you're +2, they're -2. Overall, the average difference is 0. I didn't have an effect, right? Meaning some people got more, some people got less, but they didn't go in the same direction. I've got no effect. For within subject design, that difference between groups, people need to differ overall in one direction more than the other. When that happens, now I've got evidence that my independent variable had an effect on my dependent variable. And again, in this type of design, each person serves as his or her own control. You're comparing you to you rather than you taking the drug to somebody else not on the drug. Well, again, what if it's the speed reading thing? We've got a drug for speed reading. That's weird. But say that I do. And I had a very small study, just 2 people. So it's you getting the drug to make you a super speed reader, and this other person who didn't get the drug just so happens they're a super fast reader, and maybe you have some dyslexia. So we give you the drug, and it helps you, but we can't see it because now you're reading at the same level as this super speed reader who didn't get the drug, and we conclude there's no effect, right? So that extra little bit of error, because you're not comparing people to themselves, you get rid of that within subject design. Now you're comparing you to yourself. So it's a more powerful design. You can still have multiple levels of the IV. Right? We often think of these as just being pre-post, right? So I'm going to measure you, give you the drug, measure you again, compare you to before and after the drug. But you can do before the drug, after the drug, 3 months follow-up, 6 months follow-up. I can do before the drug, after the drug, give you double the amount of the drug, see what happens now, right? There's all kinds of things you can do with within subjects design, similar to between subjects with multiple levels of the IV for the same types of reasons you would have multiple levels in a between subjects design. The advantages of within subject design, primarily it's power. It's a much more powerful design. You can detect smaller effects because you, again, using people as their own control, it cuts out a lot of error variance, right? Because you pre to you post, if it's a short amount of time, like if it's a year, okay, there's error variance can go on. But if it's, that same day, there's not many reasons you should be different from, 3 o'clock to 3:30 other than what they did to you in that experiment. And so if you're different just a little bit, we should be able to see it, right? So it's more powerful. Related to that, there's a reduced need for sample size. You can have an equally powerful study within subjects to between subjects with half the people, right? So that's obviously a cost advantage. However, there are disadvantages, and primarily it has to do with order effects. A couple types. Carryover effects are whenever you have one level of the independent variable has effects on you, and then they go to give you another level, and the effects from that first level are still affecting you, right? So we give you some drug, we see how anxious you are. Okay, let's give them twice as much, see how anxious they are. Well, you haven't returned to baseline anxiety yet from the first drug, and now you're already getting the double dose, so you are going to look even more anxious, right? Or maybe you return to baseline, but now your receptors have all been sensitized, so even with a little bit of drug, you're going to be anxious already, and they're giving twice as much, so it's going to distort the effects, right? So how would you deal with carryover effects? Well, obviously, increase the amount of time between levels, right? So we'll give you the drug today, measure, come back next week, we're going to give you something else. Practice effects. This has to do with a lot of times studies in cognitive psych. We're looking at abilities, memory, things like that, where if people are going to be doing a task multiple times, so do this task, okay, teach you the intervention, do the task again, teach you something else, do the task again, teach something else, you should be getting better at the task regardless of what they're doing to you, right? Because of practice, you're more familiar with it. You're more comfortable in the setting. Oh, I click here and I do this thing. Oh, and then the tone's going to come. I got it now. So you're going to be getting faster. You're going to be getting better. So how do you deal with practice effects? Well, obviously one thing, you could have few levels of your IV, just 2 levels, not much chance for practice. Or whatever the task is, you can have people practice it a lot before you start manipulating the IV, right? So if it's some maze where you think you can do something to help them run the maze better, have them do the maze 10 times before you manipulate the IV. That way they've kind of maximized any practice effect. They're not going to get any better from practicing. Now if they get better, it's because of what you did. Fatigue effects. This is kind of the opposite. Instead of getting better because you're doing something more, you get worse because you've been doing it over and over again, and literally because you're getting tired, or more frequently because you're just bored. That's still referred to as a fatigue effect. I'm tired, so I'm not going to really pay attention anymore, and I'm going to click randomly or type random things because I just don't care anymore. So obviously you want to shorten your trials as much as possible to reduce the impact of fatigue effects. Similar but not the same thing are sequence effects. This is where, let's say we were showing you pictures of people that are either young or old and attractive or unattractive. So you've got young, attractive, old, attractive, young, unattractive, old, unattractive. Right? And if getting those pictures in a certain order before I have to make these decisions about, okay, all these people committed a crime, how long should they go to jail for? Right? If getting the young, attractive first causes you to kind of anchor and adjust and it affects your decisions when rating the other pictures, well, that's a sequence effect. Whereas, if you hadn't gotten the young one first, if you gotten the young one last, well, then it would have been a whole different set of data. Well, then that's a problem. It's a sequence effect. So that means I need to give people different sequences of the stimuli. We'll talk in a minute about how to do that. But one more order effect to think about is sensitization. And this is where repeatedly exposing people to the dependent variable measure can sensitize them to the hypothesis, right? So if and again, maybe it's usually more of a problem if I'm trying to hide what I'm trying to do. Like I don't want you to know that I'm trying to make you a faster reader. But if I keep saying, okay, read this, ready, go, and I'm timing you, that's kind of weird. Okay, I'm going to time you again, see if you can go now. Oh, you time me again? I think you see how fast I am, right? Or if you say, how depressed are you? They do something, how depressed are you now? Oh, you want me to be a different type of depressed, more or less, right? So they can start guessing what you want them to do. Even if they're wrong, it's going to influence how they respond, either increase or decrease their score on the dependent variable because of this sensitization. Just from repeated measure of the DV causes a change in that measurement. So one way to deal with a lot of order effects, particularly sequence effects, is counterbalancing. And you do this to distribute or measure the impact of order effects, right? So if let's say you've got 3 different stimuli you want to expose people to, A, B, and C. You don't want to give everybody A and then B and then C because, again, maybe practice effects, maybe fatigue, maybe sequence effects, maybe some carryover effects. So what you can do is give people different orders. Some get A, B, then C. Some get A, then C, then B. Some get BAC, BCA, CAB, CBA, right? And when you have a fairly small number of stimuli, you can give all possible orders. When you have more than 3, then you got to go fancy something like a Latin square design, which I won't go into right now. Just know that there's a way to mathematically create a more random pattern of presentation of levels of the independent variable. And when you do that, again, if there is a sequence effect, it won't necessarily get rid of it. Like if A coming before B causes a different thing, well, you're still going to have some sequences that have A before B. But if not all the sequences are A before B, now you can test, you can measure and say, okay, are there differences in the DV depending on what sequence they got? And you hope they're not. If there are, then you got to add that to another level of your analysis. The other thing you can do is just assume that, okay, even if there are, that won't be for everybody. And so if I see a difference between A, B, and C overall, it should be due to the actual differences and not just that sequence effect, because not everybody had that sequence. And if only a fifth of the sample had that sequence that's pushing this one effect, it shouldn't be big enough to cause a thing for the whole group. So again, you're distributing the impact of the effects, and/or best practice is to measure, well, were there order effects? And if so, then you've got to deal with it statistically. Okay, evaluating experimental designs. Experiments are the best method for evaluating if a cause and effect relationship can exist. So can doing this thing, manipulating this IV, can it cause a difference, a change in this DV? Doesn't necessarily mean that that effect exists in the wild, in the real world, right? Especially doesn't mean it exists the way you found it in the lab, right? If we give, you often read about this, they say, oh, eggs cause cancer, sugar causes cancer, whatever, everything causes cancer. And often if you read the study, it'll be, we gave these rats 2 million milligrams of this substance and they got cancer versus ones that got 0 milligrams. Okay, well, in my everyday life, how many milligrams will I typically be exposed to? Oh, 17. Okay, well then why am I worried about this 2 million, right? It's an unrealistic comparison. But again, if 2 million can cause an effect, does that mean 17 won't? We don't know, but it might. If 2 million can, 17 might. So again, the cause and effect thing is important, but we have to know exactly what they studied, right? What level of the IV were they looking at, and how generalizable is that finding outside of the study, right? So internal validity is important, but then when you think about applying it to yourself, you got to think about external validity. So most of the steps you take in an experiment are to increase internal validity. And most of those things you do to increase internal validity will necessarily lead to a decrease in external validity, right? We're talking about that, control, exerting experimental control, trying to make things as similar as possible to those groups except for the IV, and trying to keep all these other things from affecting the DV. So you're in this kind of artificial lab-like environment. Well, the more artificial it is, the more confident I am about cause and effect, but the less confident I am that what I find applies outside of that lab, right? So I get more confident about cause and effect, less confident that cause and effect extends beyond the study. Whereas again, my bias is that's fine. Find the cause and effect, be confident in it, and then do another study differently to look at the other aspects of external validity. Another thing to think about, though, in terms of the utility of experiments is that many kind of interesting independent variables can't be ethically or practically manipulated. Like we want to know about, oh, what's the cause, what's the effect of this thing? What's the effect of getting married on self-esteem? What's the effect of graduating college on this? We can't assign people to groups, we can't manipulate those variables. So you can't do an experiment on some of those really interesting things, right? And that's, again, where correlation studies have a role to play. And one thing to keep in mind, though, is whenever you have something that, wow, really, I want to know about the effect of this thing, I can't look at it experimentally, but what's the mechanism that I think is at play? And let's say, graduating college, does that lead to a change in awareness? Well, what's the mechanism you think about going to college that might lead to a change in awareness? Because you might be able to measure that mechanism in a lab setting, if not the full event of going to college, right? So if you get real kind of granular, you might be able to do something in the lab still and apply experimental design. Okay, take home. Emphasis for experiments is obviously on internal validity, right? Internal validity first, external validity second. Got to be confident that the cause and effect in the study is true before you can worry about extending it beyond the study. Big emphasis in experiments is on taking away all those alternative explanations, right? I've got to rule out that, oh, well, the groups already differed, or, yeah, you found they were different on this DV, but that could be because of this other thing, not because of what you did. So everything you're doing is trying to rule out those things, right? Which reminds me of that kind of Sherlock Holmes quote, Sir Arthur Conan Doyle quote, once you eliminate the impossible, then whatever remains, despite how improbable, is true. And that's what you're doing in an experiment, right? You're eliminating the impossible. Well, it can't be different because of this, can't be different because of this. The only thing left is, hey, what I did to them, the independent variable, therefore it must have caused this change, this difference in the dependent variable. So experimental designs are very powerful tools at looking at cause and effect, but again, they're also limited to particular questions, and often limited in terms of external validity. Okay, that's all for now. Take care.